Okay, so to start with, I would like to make a correction to a mistake in the previous lecture. So thanks to my question by Manoy, I, I pointed out this mistake. So the setting, so we have a group scheme, and we have two morphisms from some X into G, and we want to define the transporter of U into V. And so we consider the scheme P, which is a fiber product. And the claim is that some, some, so the claim is that some the virus friction from P to G of some P prime. Okay, and so in the lecture, there was defined some P prime. It was a closed subscheme of this one. And so the claim was that this is represented by a closed subscheme of G. Okay, so this is okay, and of course both G lies over S, and so this one lies also over S. So there was some confusion in my lecture. So of course G prime lies over G, but if we consider some G scheme T, then as Madame said, uh, so if we have a map from T to G, it is a G prime point if and only if this map actually factors through G prime. And so if we fix this, then G prime of T is either one point or the empty set. So it's not very interesting. So one should really consider the the points of G prime in any for any S scheme T. Then we have what so G prime of T is a set of those G in G of T. And then there was another mistake that I made. So we have two maps. So we have two maps from T cross X to T prime T. And so one is simply V. And so let me just put VT since it is V extended by base change. And the other one is, so let me write UT. And we have our G, which is a T point here, so it acts on G here. So here it makes sense to conjugate. And so the condition is that these two coincide. So because those J such that so that we have GUT. So the conjugation of UT is equal to VT. And so this means that for any T prime over T and any X in X of T prime, we should have G times U of X times G inverse is equal to V of X. Okay, so the other day I took X in X of T and I was uncomfortable about this. And so, yeah, so the correct thing is that, so you want to transport one morphism into another. So we must have this equality as morphism. And so this means that they coincide on arbitrary point over another base scheme. Okay, so these are the two corrections I wanted to make. And now back to lecture 13, which is existence. Étale locally of maximal tori in reductive progress. Okay, so the proof is not easy, as you will see, and if you remember, so there was a first argument using finite subgroups of a torus, and so this is really a necessary step. Actually, there exists three proofs, at least of this. And so the original proof is Grothendieck proof, so which is in SDA 3. It's long and difficult, long and hard. And so the proof is that the functor of empty subgroups of G is representable by scheme. And so this uses finite subgroups of tori in an essential manner. Okay, so this functor is a bit frightening because it has many connected components because well, we just say like, okay, we consider the functor that to a scheme we associate the set of all subgroups of multiplicative type. Okay, so first, for any abelian group, you consider the multiplicative groups of type this abelian group, and you can consider the subgroup of G which are multiplicative of this type. So the connected components are parameterized by the set of isomorphism classes of abelian groups. So it's a huge scheme, and well, okay, of course, one can restrict oneself to the connected component which corresponds to maximal tori. But the proof that this functor is representable is very hard because it uses a representability criterion by Grothendieck that was published by Moore in a Bourbaki seminar. And it applies, in fact, it applies well to finite subgroup of tori. So the proof is going back and forth between what you want to prove. So there is a list of conditions in Moore talks that you have to check that they are satisfied, and so the proof goes back and forth between the case of a tori and finite subgroups. So it's very technical, and finite subgroups of a tori of a torus are used in an essential manner. And now there is a second proof, a variant of the same. In a course, in a course at Rimini by Brian Conrad. Yes, but yes, but he makes a short, well, what he considers as a shortcut in Grothendieck's proof. He uses algebraic spaces, of which well, I don't know anything about algebraic spaces, so I'm reluctant to to present a proof using this. So basically, his viewpoint is that if you use algebraic space, it's easier to prove that the functor is an algebraic space. And then there are criterion by Artin and Knudsen to prove that an algebraic space is in fact a scheme. And apparently, it's easy to check that in this case, it is a scheme. So it is certainly shorter, but you have to know, to learn the notion of algebraic space. And so the third proof, which I'm going to give, third proof by so. Okay, so the proof is for a general, well, it's like a smooth affine group of a general base. But de Mazure found a shorter proof for G reductive. So it's a bit less general, but this is the groups. These are the groups we are interested in. So de Mazure found a shorter proof, which is the one so this is an expose 19, proposition 6.1. So this is the one that I'm going to present. It's not entirely out of the group, because so this shorter proof builds on ideas of Grothendieck in expose 12. So I think that Grothendieck first proves the representability in expose 11. And then he kept thinking about it, and he proved some other things, and well, he proved some, well, he had some new ideas also using finite subgroups. And building on these ideas, de Mazure gave a shorter proof, more or less self-contained, and this is the one that I'm going to present. So it's no surprise that it uses in an essential manner the finite subgroups of Tori, because it seems to be the key ingredient in every proof. Okay. So what we did so far? So recall what we did last time. So we have a local Hamiltonian local Prickly Mendelian ring. Okay, so M is maximal ideal. And K is a residue field. And so the assumption strictly Insenian means that the residue field is separably closed. And so the theorem is, okay, and we call S the spectrum of this Noetherian local quickly ensemble ring. And the theorem and so I denote by S naught the close point. Okay, so the theorem is, so let G be a smooth affine S group such that we make an assumption which is slightly weaker than being reductive. Each maximal torus of the geometric closed fiber equals its own normalized, centralized. Okay, so this is true. For example, so this is true if G is reductive. Okay, because we know that in a reductive group of an algebraically closed field, maximal tori are their own centralizers. Okay, so what did we do? So proof. So let T0 be a maximal. Hmm? Hmm? Oh, yes, sorry, I'm sorry. Uh, the conclusion is then there exists maximal torus T of G, and well, moreover, it has to be split. So, okay, so the result we want to prove is we want to construct a maximal torus in G. Okay, and so for shortness, so this fiber, let us denote it by, well, no, okay. So let T0 be a maximal torus in G0. And so this exists since K is infinite. Because yep. Yes. Yeah. Yes. Any affine smooth group. And so the proof is, well, this functor is represented by a smooth scheme, and so there is an étale section. Okay, so, but the proof of the theorem is, yeah, it's, yeah. So the trick in the Mazur proof is to use this special property of reductive group, that then the sort for maximal tori happen to be their own centralizer. And then there is a trick that it is easy to lift centralizers of finite subgroup, and this will give the result. So this is really a shortcut in of the proof in the general case. Okay. Other questions? Yeah. Because the residue field is separably closed, and and in fact I prove a stronger result in a previous lecture. I proved that over an infinite field there always exists a maximal torus. Okay, so we have a maximal torus in the closed fiber, and one has so it is equal to its own centralizer because this is true over the algebraic closure. And the formation of the centralizer commutes with base change. So since these two become equal over the algebraic closure, so this is already true over the field K. So we have this this property, and so the first part was fix and some integer m, which is invertible on S, and so the first reduction was that for H large enough, and hmm? Yeah, this is a faithfully flat descent. Yeah, because it's yeah, you go from K to the algebraic closure, and it is true over the algebraic closure, so it is already true. No, it is just faithfully, yeah. But no, because K is already separably closed. Okay, well, so this is true over K because it, and so what we saw the other day, so we saw that there exists H, an integer n large enough, so that if we set n equal to m to the h, so let me continue here. Yep. So this is what we knew, but this is equal to the centralizer of the finite subgroup of n torsion point. Ah, okay. And I should say here that since K is separably closed, and any torus becomes split of a separable extension, so T0 is already a split torus. So it is Gm over K to some power D. Okay, and so the n torsion here, so this is just mu n K to the D, and we are going to call this E0. Okay, and of course we can lift E0 to the analogous scheme of S. So let me call simply E. So this is mu n over S to the D. And it turns out, since M is invertible, so this is the same as the constant group. This is also the same thing as this. And so the fact is then that if we consider the functor, which I denote by P. So this is the functor. So I write form underlined as a functor of homomorphism of S groups from E into G. So this is represented by a closed subscheme, closed subscheme of. So okay, where Ng is a fiber product well, so we have the map from G to itself, which so this is the nth power map. And here we have the unit section. And so the set of n torsion points is this fiber product. Okay, so G is not commutative. So this map is not a group homomorphism. So it's not really the kernel of something, but it is a closed subscheme because it is obtained as a fiber product. Okay, and so the n torsion elements in G, so they form a closed subscheme, and so we have that. And so the argument was that the functor of morphism from this constant group into G, this is represented by this closed subscheme. And if you take as the morphism from D copies of this, you get the closed subscheme of the default tensor, the default product of this consisting of D tuples which pairwise commute. And so this is the reason why this is a closed subscheme. Okay, because and further, so P is smooth by, I think it was my lecture 7 in August. So it is this. So these things about Hofschild homology and lifting of morphism from a group of multiplicative type. Okay, so it's always true that this functor is formally smooth, and in this case we are happy because it is a scheme, so it is a smooth scheme. Okay, so. And so we had because so you have this thing here. So these are D copies, and so you consider all the morphism going to G. So let's call it phi ij. So this sends. So this is a map that sends a dituple to G, I, G, J, Gi inverse Gi minus 1. And we want this to be the unit element. So again, the kernel of this is a closed subscheme because you make the fiber product with the unit section. So the condition that that I and J commute is a closed subscheme, and so you take this intersection of all of these. Okay. Okay, so this is closed, and so we add uh, uh, we add a group homomorphism, and actually it was a closed dimension. So let U0. So E0 was the torsion, the end torsion in the torus, and okay, and so this is contained in G0, hence U0 can be viewed. So it's an S0 point of this scheme. So it's a morphism from E to G over the closed fiber. And since P is smooth, S is Henselian, and therefore U0 lifts to a point U in P of S. Yeah, exactly. This is a cheap version of the hard Grothendieck result, but which again his proof goes through things like this. And so the trick is just we just fix, well, so this one works, and we don't have to consider the big function. Yeah, so this is, but well, this is not the end of the story. There is still some work. Yeah, it's because okay, so we get and so we get a morphism of S groups, F group schemes. So U from E, so which is U G. Okay, and well, here I just make a side remark. So it turns out that U is actually a closed dimension. Because U0 is, but this is not really needed. Okay, so so the important thing is, so now we set H, the centralizer in G on this morphism. And this is by what we proved previously, it is a closed subgroup of G. And I'm sorry, I didn't get the question. Yeah, yeah, yeah. Yeah, it requires some finiteness hypothesis, but uh, S is a Noetherian scheme, and so everything inside is a finite type. So there are no finiteness issue. Uh, but yeah, but and moreover, we can it is true that it is a closed immersion because the kernel is a group of multiplicative type whose closed fiber is a unit group. So actually, so it is certainly a monomorphism. And then again, there is this result that a morphism whose source is a group of multiplicative type. A monomorphism from a group of multiplicative type is a closed immersion. So, but so this is okay. And mm, yes, yeah, yeah. Well, I can say it's Nakayama. Yes, you're right. Okay, but so we just take the centralizer, and so the closed fiber is a centralizer of U0. And so this was this. And so this was the centralizer in G0 of 0. And so this is the torus T0. Okay, so H is a good candidate to be the to be okay. And now there is a difficult theorem of okay. So we have reached that point, and now we're going. Well, so of course the idea is that if we take the connected component, uh, uh, the idea that the connected component is the sort for maximal torus. Okay, so let me be precise about this. So this is indeed true, but this needs another theorem that I'm going to write. Yeah, well, it is a so it is smooth because we saw that when we take the centralizer uh, the centralizer of a group of multiplicative type, it is smooth. Okay, and so the theorem, so hmm? uh, no, no, no. Okay, so let me, okay. So, well, actually, I said it. So, so consider that we have proved that this is a closed immersion. And so E is a closed subgroup of G of multiplicative type. Okay, so then this H is just the centralizer. And since this one is of multiplicative type, the centralizer is smooth. No, no, it need not be. We will see that it could be, well, there are few possibilities, but it need not be of multiplicative type. Um, but now there is this theorem. So So let me call this proposition. Ah, okay. So let me say that, well, let me not state the theorem, but so let me say that by some results that I will prove later, theorem 4. H, so this H that we are considering, and so which is such that H0 is a torus. So there is a theorem which says that it contains an open and closed empty subgroup. Let us call it T. Such that, so whose closed fiber is that of H0, so which is T0, so which is a torus. Hence, E is a torus of dimension D. Okay, so we assume that we assume this given, and we just prove that it is a maximal torus, and then I will prove this theorem, which is very tricky. Okay. And now we want to prove that T is a maximal torus of G. Yeah. Yes. Yes. Yeah. Yeah. It is H naught. So in general, it is an open and closed subgroup, but it is connected, so it has to be the connected component of H naught. And so to prove that T is a maximal torus, but consider again the centralizer. So let C be the centralizer in G of T. And again, this is a closed Morse subgroup of G. And by the classical, well, I'm not even sure, but oh yeah, by the classical theory, we know that the fibers of C, well, I'm not even sure we need this sentence, are connected. So in fact, so we know that T is a closed subgroup of its normalizer. And they have the same closed fiber. And so we are over the spectrum of a local Noetherian ring. And so I think that is implied already by Nakayama. We actually get that T is equal to C. Let me see. Yeah, I think that we don't even need this because, so this is a closed subgroup, so it is defined by some ideal. And so if we mod out the maximal ideal, the ideal becomes zero, so the ideal was already zero. So we have T is equal to C. And now, so this implies that T is maximal torus because in each fiber it equals its centralizer, so it cannot be contained in a larger torus. Okay, so this sentence was part of the proof of De Mazur. Yeah, so De Mazur, the end of the argument was that, well, both are smooth connected and they coincide at the close point, so they coincide. And I think his idea was an argument of dimension. But I realized that since we are in the local case, we could as well use Nakayama. Okay, so we have proved the theorem. If we assume this marvelous result that if you have if you have a group such that the closed fiber is a torus and it contains something. So let me start the proof of this, which is interesting in its own right, but well, which is rather long. Okay, so the proof is complete. So the proof is complete so far up to the proof of well, of this theorem 10. Okay, so hmm? Yeah, okay, so ah, yeah. Okay, so the theorem I was looking where I wrote in my notes. So this is this. So we keep notation. Well, so A Mosserian local and salient ring as its spectrum as its close point. And let us change notation. So now let G be an affine smooth S group of finite type. Flat over S, and such that the closed fiber ah, is multiplicative type. Okay, then there exists an open and closed immersion H into G, where H is an isotrivial empty group over S, so let's call it used one, such that US is an isomorphism. Okay, so this is a change of notation. So this is a change of notation because now the G is the H of the previous proof. Okay, so we will apply this. We'll apply this to G, which is a centralizer. So this was the previous, the one that was previously called H, and the H given by this last theorem will be the T. Okay, so I'm changing. Well, I'm changing the notation because I'm running short of letters. Okay, so when we started with G reductive, we want to construct a maximal torus. And we have this intermediate group, which is constructed as some centralizer. So it is a smooth, a finite type. G is affine, so it is affine. So it satisfies all the assumption here. It is yeah, actually smooth is not needed here because otherwise flat would be yeah. So here we just need that G. So we need a finite type and flat over S. So this is the case for this H. And the closed fiber is a group of multiplicative type, which here is a torus. And so the conclusion is that H contains an open and closed subgroup of multiplicative type, which has the same closed fiber. So this is a theorem that we want to prove. And now we change notation. And now H becomes this G. And the group of multiplicative type whose existence is claimed will be called H. Okay, so this is just a change of notation. But this is the notation that was used in my lectures in August. So this is, okay, so do you agree that if we prove this theorem, then we will be complete with the proof of the existence of maximal tori in a reductive group? Okay, so let's, yep. Yeah. Yeah, T naught is a torus. Yes. No, it's a consequence precisely of this result. The rigidity of yeah, 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 yeah. But the proof is the proof I know goes through this theorem. No, no, no. Uh, I almost proved this, but not. I didn't do the hard part. What I prove is that yeah. What I prove is that if we have a morphism between two groups, if we have two groups of multiplicative types, and then it's important, it's much easier if the target group is of multiplicative type, as you will see in the proof, then any morphism on the closed fiber lifts to a morphism on the whole thing. But when you make no assumption on the target group, the proof is really much harder. And so this is the proof I'm going to explain. But indeed, as a result of this, there is this rigidity result, which is also which is used by de Mazur at the very beginning of volume three of SGS3, that if you have a smooth group scheme, if one fiber is reductive, then it is reductive on the neighborhood of that fiber. But the proof relies on the existence of a maximal torus, because you have a maximal torus, then which you can assume to be split. Then you look at the Lie algebra, and it is a you have the root space decomposition, and they are line bundled, and so they exist locally, and then everything goes fine. But so the key result is the existence of a maximal torus. Okay, so let's prove this theorem in several steps. So I will not finish today, but let us just start the proof. Okay, so this theorem was proved in August. Proved in August in the case where G itself is empty. And so we are going to reduce, and the reduction is not easy, to this case. Okay, so let me recall the argument. So if, well, well, so this will come in the proof. So let's so so first step in the proof of in the proof of theorem. So let A prime be the M-adic completion of A and okay, so let S prime be the spectrum of A prime and let G prime be then by base change. Okay, so by the cohomological results of the lecture in August, we can lift from the closed fiber um, there exists H prime, S prime group of multiplicative type, isotrivial, and an open and closed immersion H prime to G prime, inducing an isomorphism. On the closed fiber. Okay, and also there is an equivalence of categories between isotrivial empty groups over S prime, S0, and S. So this is also contained in the lectures. And H primes come from an isotrivial empty group over S. Okay, so since, well, isotrivial means they become diagonally a double group of a finite étale extension. And since S is Henselian, the category of such group of S is the same as the similar category of the closed point, and also in this direction. Okay, so we have all this, and so we are reduced, to prove that the natural map from S groups from H to G to S prime of H prime G prime is projective. Okay, so this is the key point. Okay, because of the cohomological result okay, so over the closed fiber, HS is a group of multiplicative type, but over a field, any such group is isotrivial. So we have here an isotrivial empty group. So it comes from a group over S, and so we have a more, well, and well, so we have a morphism at the level of closed fibers, and by the cohomological result, we can lift this to infinitesimal neighborhood of the closed fiber. And so we have a projective system of morphism. And so we have, so we have seen in August that we obtain something at over the completion of the local ring. And the object comes from object over the Henselian ring itself. And so the key point is to prove that the morphism, which is obtained over the completion, that it does come from a morphism here. And so this will be the hard work of the tomorrow lecture. So let me remind you, so when G is of multiplicative type, the proof is very easy and beautiful, because we just look at the torsion points, the end torsion in well, okay, so this is bijective. So we consider the two maps here. And so we know that the morphism, so this is faithfully flat. And so we know that the image, so this map is an inclusion. It's always an inclusion. And the image is a subset of the morphism here, whose two images they coincide. And if G prime is also of multiplicative type, well, now the torsion subgroups in H are schematically dense. So it's enough to check that the two images here coincides over the torsion. But now, if this one is of multiplicative type, the end torsion there goes to the end torsion there, and both groups are finite over the base. And again, the Henselian property tells us that we have an equivalence of categories between finite empty groups over S and S prime. So in this case, we know that every morphism descends. The proof is crystal clear in this case. And when G is not assumed to be of multiplicative type, it's not even assumed to be commutative. So the trick is to prove by hard work that actually the if we restrict to an end torsion subgroup, somehow there is an image scheme, there is an image which is a closed subgroup of multiplicative type. And okay, so this is a tricky and technical, and so this will be done tomorrow. Okay, so let's stop here. And so tomorrow we finish this proof, and then I will review the things about root systems and root subgroups. Hmm? Yeah, a finite flat. No. It need not be, no. So there is an example in expose 19. One such example, so over the affine line, one can consider a group which is SL2 everywhere except at the origin. And at the origin, it degenerates to a solvable group. And then one can take but this group has a maximal torus, which is one-dimensional. And and the closed fiber is solvable and disconnected. So if we remove the non-neutral component, we have a strange group, and then an example of such edge could be the normalizer of the torus in this group. And so so outside the origin, T has index 2 inside its normalizer. But at the origin, the normalizer is H itself. And so basically, yeah, so the G that can occur, so if H is going to be a torus, the torus has to be normal inside G. So so you can think as G of some the normalizer of the torus in a reductive group, but you may remove some points to yeah. So in fact, there are very few possibilities, but the proof is incredibly difficult, at least to me. Okay, so we finish this proof, and then we go for root groups and line groups and everything. Okay.